Today, guys, we start chapter 7, chemical reactions. Okay? Now let me remind you, as we think about chemical reactions, about what a chemical reaction is. Okay? A chemical reaction is a chemical change. It's a change in composition and or structure. If you have a change in composition, you absolutely have a change in structure. There are some situations where you can have a change in structure without a change in composition. Okay? But no matter what, when a chemical change happens, you end up with a new substance. A physical change is a change in appearance without a change in composition. So it's like going from liquid water to solid water ice. I still have water. It's got the same composition. It's got the same chemical properties, okay? So cutting, folding, melting, freezing, evaporating, all of these are physical changes. So, how do we know there's been a change in composition? Well, think about the reaction, the lab we did where we looked at those series of reactions. And we noticed that we had a change in composition because we had a change in physical properties, like going to be a gas or becoming a liquid or becoming a solid. And we have changes in chemical properties. So when a chemical reaction happens, we create new substances that have different properties. Okay? So physical properties, remember, are melting point, boiling point, color, sublimation point, workability, state of matter, all of these things. Now, we're not going to worry about conceptual problems 7.1 and 7.2. You can look at those. Those are bunny hop easy. Okay? So let's look at writing a chemical reaction. When we think about writing a chemical reaction, what we're doing is we're writing a recipe. And we're doing it in the form of something called a chemical equation, a one-line recipe. Now, being from the Western world, we read right to left. Our chemical recipe, our chemical equation, is going to read right to left. So let's think about the things you find in a recipe. Okay? In a recipe, we find ingredients, that we find what we're going to make. In chemistry, we call it the product. We find amounts. You sometimes find times and conditions, like soften the butter before you beat it into your cookie. In chemistry, we're going to see things like our states of matter: gas, liquid, solid, aqueous, lowercase g for gas, lowercase l for liquid, lowercase s for solid, lowercase aq for aqueous, which means dissolved in water. There are some more that you're going to hit when you get to organic chemistry, but we're not there yet. So all of these things are found in a chemical equation. Now, the ingredients we're going to call reactants, and they're going to be on the left-hand side of an arrow or a set of arrows. The products, what we're going to make, are going to be found on the right-hand side. So let's look at this chemical equation. This says I'm going to take one molecule of CH4 in the gas phase and react it with 2 molecules of oxygen in the gas phase to create 1 mole of CO2 gas and 1 molecule of CO2 gas and 2 molecules of oxygen in the gas phase. The double arrow here indicates that this reaction could run in either direction, but we're running it from methane and oxygen to CO2 and water. Okay? So reactants here are on the left, products are on the right. Now, the numbers out in front of each one of those substances is called a coefficient. And the coefficient tells us how much. Now, I read this thing off in terms of molecules. We can also read it off in terms of moles. I could say 1 mole of methane, CH4, in the gas phase reacts with 2 moles of oxygen in the gas phase to give me 1 mole of carbon dioxide in the gas phase and 2 moles of water in the gas phase. Okay? I can read it on a molecular level. I can read it as a molar amount. Now, when I look at this, one of the things about a chemical equation that we've got to pay attention to that you don't necessarily pay attention to when you're cooking in your kitchen is that all chemical equations have to obey the law of conservation of mass, which says, remember, matter cannot be created or destroyed. In a practical sense, okay, let's see where our display went. Okay, it's back. No matter what you guys are woogieing with the system, I'm not stopping yet. Okay? So, in a practical sense, what this means is that the number of each type of atom on each side of the chemical equation has to be the same. So if we look here, if I've got one methane, I've got one carbon. If I've got one carbon dioxide, I have one carbon. I have 2 times 2, 4 oxygens. I have 2 oxygens here, 1 times 2, 2 times 1, 2. 2 plus 2 is 4, there's 4 oxygens. I have 4 hydrogens here, 2 times 2 is 4 hydrogens here. When everything matches on both sides of the chemical equation, we call this a balanced chemical equation. Okay? So we've checked this one for balance. Now, when we think about balancing a chemical equation, sometimes we'll be given an equation that's just got the reactants and products and it doesn't have any of the coefficients. And we've got to figure out the coefficients. The process of balancing a chemical equation is a loose process. So let's talk about how we do it. Okay? First thing you want to do is you want to make sure that you've got all of your reactants and products listed. Note any element that stands alone. Okay, a pure element like just oxygen or just hydrogen. That's going to be the last place I give a coefficient. I want to pick an element that appears in one compound on both sides and assign coefficients to those two compounds so I balance out that element. If you set the number of a second element on one side, then go and balance that one on the other side. And then if that sets an element, you go and balance on the other side. You're going to go back and forth balancing elements until everything's got a coefficient and everything's balanced. Okay? Now, one of the things I want you to note is if you've got a polyatomic ion and it moves as a unit, you want to balance it as a unit. That's going to make your life a gazillion times easier. You want to check equations for balance by checking the number of each element listed on both sides and clear any fractions that might have appeared in the balancing process. Okay? Now, fractions when you're balancing are okay because at the end we're going to clear them out. And remember that an element doesn't count in the side on a side when you're balancing until that member of the reaction has a coefficient in front of it. Okay? So we're going to look at some practice problems. We're going to look at practice problem 7.1 on page 293. Okay. Okay. Let's see. Ah, over a page. I was about to say, that's not what I wanted. Okay, it says, write a balanced equation for the reaction between solid silicon dioxide and solid carbon that produces solid silicon carbide and carbon monoxide. Okay, so this one's given to us in words. So if we look at the words here, it says that we're starting out with solid silicon dioxide, SiO2, solid, and it's reacting with solid carbon. And we're going to silicon carbide, solid, and we're going to carbon monoxide gas. lines in front of each thing so I know that I'm putting in coefficients there. I have to fill in all those lines. Now look at this. Notice that carbon appears 3 places. So carbon's going to be the last thing that I deal with. And I've got pure carbon here, so this is the last place I'm going to put a coefficient. I can either start by balancing out the silicon or balancing out the oxygen. It shouldn't matter. Okay? So I'm going to start with the silicon. I'll put a 1 there and a 1 there, and I've balanced out the silicons. Now by putting a 1 there, I've locked myself into 2 oxygens. So I put a 2 here to balance out my oxygens. Now on this side, I've got 1 silicon. I've got 1 carbon. No, I see 1 carbon and 2 more carbons. I've got 3 carbons, and I have 2 oxygens. Over here, I have 1 silicon accounted for and 2 oxygens accounted for. There's no number there. I don't have the carbons accounted for yet. Well, I need 3 carbons. So it means I need to put a 3 there. So I now have 3 carbons. So I have the same number of each element on both sides. That means it's a balanced chemical equation. Okay? Now, let's look at the second one. All right, guys, start reading that second one. Okay, so if we look at it, we're told we've got the combustion of ethane, C2H6. Let me see if this thing will focus a little. Let's see, focus, where's the focus? Let me blow it. Ah, that's better. Okay, C2H6. We're doing the combustion reaction of C2H6, a minority component of natural gas, in which the gas combines with oxygen, okay, to create carbon dioxide and water. Okay, now oxygen appears in 3 places. I'm going to deal with oxygen last. Okay, and right here is going to be the last place I put a coefficient. So I can either start with the carbon or the hydrogen, it shouldn't matter. Now if I put a 1 there, I'm going to put a 2 there. So I have 2 carbons on this side, 2 carbons on this side. By putting a 1 there, I've locked myself into 6 hydrogens. So I'm going to have to put a 3 there so that I've now got 6 hydrogens. Everything's got a coefficient over here, so I've got 4 plus 3, I've got 7 oxygens. Now, how do I get 7 here? Well, the molecule oxygen is O2, so think about 7 halves. 7 halves times 2 gives me 7 oxygens. Everything's balanced. But I've got a fraction, and in balanced chemical equations, we don't like fractions. So to get rid of that fraction, I need to multiply everything by 2. So if I did that, I get 2C2H6 gas plus 7O2 in the gas phase, going to 4 carbon monoxide gas plus 6 waters in the gas phase. Okay? And that would be my final product, my balanced chemical equation. Now, let's flip to the end of the chapter and do a few more examples just so that we've got enough practice in, okay, until I feel like you guys are okay. So let's look at problem 33. I'm going to look at balancing some of these. Now I want us to start off by looking at 33B, because I want us to do an example where we see a polyatomic ion. So let's look at A and B there. Okay, I don't want to kill you with way too much. So if we look at the first one, we're combining carbon dioxide gas with calcium silicate and water to form silicon dioxide and calcium bicarbonate. Now notice there's not a polyatomic ion that moves from one side to the other. So we've got carbon dioxide gas combining with calcium silicate, which is given to us as a solid, plus water here that's a liquid, and we're going to silicon dioxide, solid, and calcium bicarbonate. Which is aqueous. Okay? Now, notice that oxygen's everywhere. I'm going to worry about balancing everything else, and then oxygen should be taken care of. So we could start with our calcium, we could start with our carbon, we could start with silicon, but the last thing we're going to deal with is oxygen. I'm going to start with calcium. If I put a 1 here and a 1 here, I've balanced out my calcium. So I've got 1 calcium on this side, I've got 1 calcium over here. Putting a 1 there locked me into 1 silicon. So 1 Si here, so I'll put a 1 here, so 1 silicon here. By putting a 1 here, 1 times 2, I've got 2 carbons. So I need to put a 2 there to balance out my carbons. Now, putting a 1 here, that locks me into 2 hydrogens. Okay, so I need to put a 1 there to give me 2 hydrogens. Now let's check our oxygen. I've got 4 here, 2 times 2, plus another 3, 4 and 3, that's 7, plus 1 more, I've got 8 oxygens. I've got 2 here, plus 2 times 3 is 6, times 1, that's 6, 2 times 6, that's 8 oxygens here. So I've got the same number of calciums on both sides, same number of silicons, same number of carbons, same number of hydrogens, same number of oxygens. It's a balanced chemical equation. Now let's look at the next one. Okay, guys? So notice in this one, I've got cobalt-3 nitrate, aqueous, and ammonium sulfide, aqueous, going to cobalt sulfide solid and ammonium nitrate aqueous. Notice that the nitrate ion appears on both sides and the ammonium ion appears on both sides. So since they appear on both sides, okay, as the polyatomic ion, I'm going to balance it as the polyatomic ion. So we have cobalt-3 nitrate, aqueous, and it's reacting with ammonium sulfide aqueous, to give us cobalt sulfide solid, cobalt-3 sulfide, and ammonium nitrate aqueous. And of course I didn't put my spacings just right, but we'll work with it. Okay, now I can start anywhere. Nitrate appears on one place on both sides, ammonium ion appears on one place both sides, the cobalt-3 plus appears one place both sides, sulfur appears one place both sides. So I'm going to start with cobalt just because. So if I put a 2 there and a 1 there, I have 2 cobalts on this side, and I have 2 cobalts on this side. Okay? Now by putting a 2 there, I've locked myself into 3 nitrate ions. There's 3 nitrates there. Well, excuse me, that should be 6. 2 times 3 is 6 of those. So 6 nitrates. Okay? I have 6 nitrates. Now, by putting a 6 there, I've locked myself into 6 ammoniums. So I need to put a 3 there. 3 times 2 is 6 NH4 pluses. Over here, I have 6 NH4 pluses. And now that gives me 3 sulfurs. And look, 1 times 3, 3 sulfurs. So I have 2 cobalts, 6 nitrate ions both sides, 6 ammonia ions both sides, 6 sulfurs both sides. It's balanced. Okay? And guys, this just takes practice. And if you ever start balancing something and it's not working, don't panic. Just erase and pick a new start spot. Okay? Not a big deal. Okay. Now, once we have a balanced chemical equation, what we've got is a powerful tool for determining amounts of materials that we can mix together to make something, and it's a powerful tool for us to predict how much product we can make. So guys, we're going to mix together the math we were doing with our intro to the mole with a balanced chemical equation. So scroll up for me. When we read a balanced chemical equation, the moles of each substance have a fixed relationship for that reaction. These amounts are called stoichiometrically equivalent amounts. Isn't that a big mouthful? Which means they have an established fixed relationship. So if we were to look at this one, I can say 2 moles of C2H6 produce 4 moles of carbon dioxide. That's a fixed relationship. Or I could say 2 moles of C2H6 need to react with 7 moles of oxygen. That's a fixed relationship. So if I was given 3 moles of C2H6, how many moles of CO2 can we produce? Okay? So let's look at this. So I'm starting out with 3 moles of C2H6, and I'm asked moles of CO2. Now, looking at the balanced chemical equation, we know that 2 moles of C2H6 produce, and the equal sign is the same as the word produce, 4 moles of CO2. Okay? Those came from the balanced chemical equation. Guys, this is another case where we have a mole ratio, a mole relationship between 2 things. So if I go 3 moles C2H6 and I use this mole ratio, I can go 4 moles of CO2 over 2 moles of C2H6. They have a fixed relationship. So notice the moles of C2H6 divide out, and 3 times 4 is 12 divided by 2. That gives me 6 moles of CO2. Not bad, right? So you could do the same thing and figure out how many moles of C2H6 could react with, let's say, 0.5 moles of oxygen. Okay? That's the next little question I've got. So now we're asked moles of C2H6, given that we have 0.50 moles of oxygen. Well, looking at that balanced chemical equation, I know that 2 moles of C2H6 react with 7 moles of O2. So if I start out with 0.50 moles of O2, use my mole relationship here, put 2 moles of C2H6 on top, 7 moles of O2 on bottom, I'm going to have 0.5 times 2 divided by 7, so 0.14 moles of C2H6. Okay, because the moles of oxygen divide out. Now, one thing I want to point out to you, okay, let's look at this balanced chemical equation for a second. When we look at these mole relationships, the mole ratios here, they're considered exact numbers because I can't have half a molecule of carbon dioxide, or I can't have a third of a molecule of water. So these are considered exact numbers. Remember that exact numbers have infinite significant figures. So they're not going to affect how many significant figures our answer has. Okay? So if I start out something here with 3 significant figures, my answer is going to have 3 significant figures. I started out here with 3 significant figures, I ought to end up with 3 significant figures. I know that's not the way I wrote it because I wrote that I had 0.50. So when you go back and look at it, you go, Ms. Vincent! I know. I was glancing from the side. I apologize. Okay? So this is an important skill for us to be able to have, to go from moles of one material in a balanced chemical equation to moles of another material in a balanced chemical equation. Now guys, this is a good place for me to stop, mainly because my battery's almost dead and I'm almost out of storage space. So we will pick up here and we're going to add to it and go from grams of one material to grams of another material. So previews a coming attraction.